Hi there, everybody. Welcome for the stream. It's great to have you here. How is your Global Hack Week going? I hope it's going well. I saw some shout outs in the chat earlier. Hi there, Shrey. Islam Farah, good. I'm glad. And Shivankar, I think I saw you in a previous stream, so welcome back. But let me send the check-in link because it's really important that everybody checks in for the event. So I'll just send that again in case you weren't able to get it the first time. That sounded kind of aggressive, actually, in case you weren't. I didn't mean it that way. I just meant if you haven't seen it or whatever the case may be, there you go. But yeah, does anybody have a favorite stream that they saw from Global Hack Week? Any mini events stand out to you as particularly fun, or any workshops that were really enjoyable to watch? Anybody want to share their experience? We're on day 4, so we still have quite a few days. I mean, we have tomorrow, all of the rest of today, and day 6. So it's still not over yet, but we're definitely getting there. All right. Well, in that case, I will just begin with our part 2 of machine learning tools in MATLAB. Woohoo! And this is take 2 because, unfortunately, for our first stream, my internet connection cut out. We had some pretty big storms here in California, and they caused a power outage in my building. So that's why, unfortunately, the stream cut short. If you didn't see the announcements or any of those updates. Rahul said, what will we do in this section? Great question. We learned a little bit about the basics of MATLAB last time. So in this section, what we're going to do is take that a step further, and we're going to train a KNN neural network. KNN stands for K nearest neighbors. Yes, the K stands for K. And then we're going to learn a little bit more about processing data in MATLAB, pre-processing, and also data stores, and how you can use large data sets that don't necessarily fit in memory, how you can use those to train your model. So that will be kind of the next step. But yeah, great question, Rahul. So let's go ahead and get started then. A quick review from last time I have here. So if you weren't here for last workshop, just try your best to answer these questions. If you were here last workshop, here's your test. Don't worry, you can't fail. There's no way to fail. There's no bad grades in Global Hack Week. It's just a workshop series, not a class. So, yeah. All right, let me check. I'm going to check into our form results here and see if anybody has responded. So if we don't get any responses, instead, what I'll do is go over the answers myself. We'll take the quiz together. I think that would be a good use of time if we took the quiz together. All right, I'll give it a couple more minutes, and then we will go over the responses together. And the first question in this quiz. Let me actually share my screen so that you all can see what I'm looking at. So the first question is going to be, what is the formula for standardizing data? And the formula for standardizing data is actually going to be the first option here, data minus mean divided by spread. And the reason we call it standardizing data is because that is related to the standard normal distribution and what we call z-scores. So z-scores are essentially how far away is your data point from the average value, from the typical value in a normal distribution. And how can we quantify that? And so that's why we use the z-score in that case. And then what is the formula for normalizing data? Well, it's going to be the other option, data minus min divided by max minus min. And, you know, other folks will give you other formulas for normalization. It's totally possible to have a different formula. But in most cases, this is the formula. And the reason why this formula is so good is because it's a 0 to 1 scale. So 0 being the lowest, smallest number in the data set, the minimum, and 1 being the largest, max minus min divided by max minus min. So it would just correspond very nicely to those. And one thing you learned from the last workshop, one thing we learned in the last workshop was why this matters. So we actually learned that the important thing for standardizing data, normalizing data, the reason why it's important for machine learning is because many algorithms in machine learning, firstly, they will weight the data differently. It's on a different scale. So by putting everything on the same scale, we're not biasing the model in any one direction. We're not distorting its ability to learn, and that's great. And this is great too. Lahaney learned that MATLAB can do ML. Yeah, me too. I didn't really think about MATLAB as a machine learning library because I used to use it before machine learning was really big. And then when I revisited it recently, I realized that there are all these great machine learning tools in there. And some of them are a lot more visual and a lot more, I would say like thoroughly explained, easier to use than more hard-coded type of solutions you might find in Python or Julia or some other language. And then, oh, hi there. Elena, good to see you again. I hope this isn't too early or too late of a time over there. I remember last time you said the workshop was at 3 a.m. That's really tough. I hope this one is a little bit better. And yeah, exactly. This is where most people use MATLAB, is mathematics class, signals class, in engineering or math. But yeah, this time we're going to do some machine learning. Yes? Okay, good. That's much better. Much better. PM, even better. That's great. All right, well, so why don't we go ahead and continue along here with our screen. And I'm going to go back to our slideshow and show another slide about what we call feature extraction. So feature extraction is what we left off on last time. And I think I gave this example of when you tell your friend directions, you're not telling your friend, hey, can you take a step in this direction and then another step and then another step and then make another step? It's kind of a waste of everybody's time to give that much information. And it doesn't help your friend any better than just saying, hey, go all the way down to the end of the street and make a right. Okay? Because that's really much less in detail, but it's the same amount of information. And that's what we're trying to do with feature extraction. We're trying to distill our data, which could have many, many, many features or dimensions. and distill that into a smaller, useful set of features that will still capture the majority of the information that we need to make a prediction. And I've just listed a few techniques that you can use to do this. One super popular technique is called principal component analysis, or PCA. And this is a linear method where you basically decompose your signal into many orthogonal. That's a little bit too complicated. You basically just distill your data into a few components, maybe 3 or 4, that can explain the vast majority of your inputs. And they are also independent. That's what I meant by orthogonal. They're independent. So each feature is going to not rely on the other one, which is how they get this maximum information extraction going. And another thing you could do is data transformation. So it's common in a machine learning paper to see that the authors have developed their own formula for some particular metric, right? Let's say they're looking at farmers, and those farmers are growing crops. Well, the data might be just about the number of crops grown on the field, but they may invent a new variable, that is the crops per square meter, and feed that as well into the machine learning algorithm. And crops per meter might be very explanatory of some feature of some target interest variable, and then that would be great. But you wouldn't get that normally from just the crops and just the area of the region. So then we also have random forest feature importance. And random forest is a machine learning algorithm in and of itself. And it basically helps you rank the features in terms of how important they are. It has this nice secondary feature where it does that by design. So sometimes folks will use random forest, impose that on their data, even if they're not using random forest themselves for the model predictions. They'll use it to get these importance metrics to see, which of these features is really making a difference. Because sometimes machine learning models can be hard to interpret. All right, so let's try it out in MATLAB. And I want to actually give a few minutes for everyone to get set up on MATLAB, because I know not everybody will be set up on MATLAB. And it takes a minute to get signed in. So go to this page, and if you're not already signed in, we're going to be going to MATLAB Academy. Oh, thank you, Elena. I will send the link. So this is the link to sign up, matlabacademy.com. And here's the link to the portal. So I'm just going to give a couple minutes for you all to get set up in this portal. All right, everybody. So hopefully you were able to get set up with MATLAB. And now we're going to actually do it ourselves and go into this Academy portal. So what we'll be doing today is calculating some features, and we're not going to be doing PCA or random forest importance. Those are a little bit too involved for the scope of this workshop, but we'll do a few feature transformations to compute new features. And so first, we're going to calculate the time taken to write a letter. Okay, so we have these times. I mean, we have in microseconds the time between the start of taking data and whatever point. But honestly speaking, the machine learning algorithm is going to have a hard time to infer that, oh, I should look at the total amount of time and that's going to tell me something. We kind of need to bring it there. Shavankar says, which one is it? This is the data transformation. So of the three techniques, this is data transformation. And the link, I sent the link in chat. Let me double send it. So this is what we could call data transformation method. Because really, we're not taking anything new. We're not adding any new data. We are just transforming the current data that we have into a more usable, information-dense form. Okay, and by doing this, we're going to really help the computer to understand what it is. Oh, wait, where did you write? I haven't written anything yet, but I'm about to. So I pasted the link to the lesson, and we're going to do task 1, which is to compute the total time taken to write the letter M. Now let me zoom in. I think maybe that might be part of the problem, is it's a little bit small. So let me just zoom in a little bit. Hopefully that will help. I don't know if that helps at all. I hope it does. But yeah, so for this first task, we're asked to calculate the time taken to write the letter M. And so we call a variable, we call it dir, U-R. And what we'll do is we need to extract the last value of the time, t. So letter.time is the time variable. And we need to extract the last one. I forget, I think the last, I'm not sure if you can do -1 in MATLAB. Let's check actually, but this should be the way to go. Might be end somehow. Okay. End, yes, end. So thank you for reminding me, MATLAB Academy. So you'll use end, not -1 like Python. Let's actually see. I don't know if -1 would work. I'm kind of curious now. Let's try it. Okay, yeah, that doesn't work, so you have to use end. Interesting. And so this is a new variable that we have done. Usha says, last time it was on commands, but it's classification workflow up there. Did I miss any part last time? Well, good question. So last time we did go over, for the first part, some commands, but then we moved into a second portion of the program, which was more about machine learning and data visualization, data extraction. So if you want to catch up on that, let me just send you, it would be in chapter 2. So this is the most recent thing that we did last time. Let me just share this with you in the stream. So I'll show you what we were doing last time. So we were doing some pre-processing on our data, which are all letters. So these letters are J, M, and V. And then eventually we'll move to include all letters. But for now, we're just doing J, M, and V. And we kind of massaged this data a little bit. We got the milliseconds into seconds. We fixed the aspect ratio. We kind of made it more readable. From its raw state, we transformed it into something a little more easy to work with. So that's what we did at the very end of the workshop last time. Oh, sorry, Elena. I guess I didn't explain this well. So you see the MATLAB interface on your computer. So I hope you can see what I've been doing here. Is you can just write inside of the tasks here, and then you can click submit, or you can click run on this top corner. And that will help you to run the codes in those cells. So yeah, thank you. No problem. Yeah, thank you for your question, and thank you for the interaction. Hopefully this is helping us get a little bit more context for what's going on, since part 2 is always a little bit harder than part 1, because some folks might be missing some of that context, or we tend to take a break. I mean, it's been a couple days since we did a stream on MATLAB, so I totally get it if folks need us to do a refresher. I myself kind of need a refresher. But all right, our next task is to calculate the aspect ratio of the letter by dividing the range of values of letter.y by the range of values of letter.x, and we will assign the result to a variable a ratio. So a ratio is equal to the range of the letter y divided by range of letter.x. So remember that to get a variable from your data frame in MATLAB, you use this dot variable convention. So you would use data frame dot variable. That's how we're doing it. All right. And so we'll just click submit here to go further. And finally, we're going to change the file name and run this multiple times. So we'll just change it to J, and we'll run to see what happens. We get a different feature here. Duration is 0.4 seconds, and the A ratio is 2.8952. So you get a different value, and let's try V now and see what we get for V. All right, and we get duration 0.308 and a ratio 2.04. I think that makes sense to me, at least, because I personally think it's much faster to write a V than it is to write a J, especially if you're going to put that little dot on the top of your J. Paste the code. Absolutely. So remember, you need to navigate to this link here, Elena, and then here is the code that you can type in. So for task 1, you would type in duration equals letter.time end. For task 2, you could type a ratio equals range letter y divided by letter x. And by the way, if you are having trouble viewing this, you can go to the task and click on See Solution, and that will give you the correct code. So you just click on that button, and it shows you all of the correct codes. That's what I like about this MATLAB Academy thing. But all right, we actually have a part 2 to this extract features that we'll move on to now. And we know that the MAT file contains a table of the extracted features for the 470 letters written by a variety of people. And so the table has 3 variables: character, which is telling us which letter it is; aspect ratio, which is the variable that we talked about and we just computed, and duration, which is the other variable that we just computed in the previous section. So let's plot these features by using the scatter function. We're going to plot the aspect ratio on the horizontal axis and duration on the vertical axis. So we type scatter, and then our MAT file is called features. So we type features dot, and the aspect ratio is on the horizontal axis. So we type aspect ratio, and then comma features dot duration. Okay, so let's try this and see what we get. All right, so you can see there's a lot of data points. There's a few data points with a really long duration, letters that took a super long time to write. And duration, it seems, or an aspect ratio, it seems like we have them all over the place, even some aspect ratios as high as 10, which is really high. That means that the y-axis was 10 times larger than the x-axis spatially when they wrote the letter. So I'm not sure if we're going to be able to distinguish between these letters just based on aspect ratio and duration. I mean, we see the scatter plot, everything is just spread all over, but we'll see. And Anushka says, MLH. Hi there, Anushka. Good to see you. Thank you for joining. And yeah, go MLH. Here we are in day 4 of Global Hack Week. Yeah. Well, okay. So why don't we do this task? Gscatter, and we're going to use the same plot as before. So we type features aspect ratio, features duration, and on this third, we're going to use the letter. So this is going to be our group. So features dot character. And let's submit it and see what we get. We should get the same plot, but with slightly different colors. And look, we do in fact get that same plot. It seems like, honestly, on the x-axis, aspect ratio is the most helpful for us. That's just based on my personal intuition. I mean, look at the x-axis variation. You can clearly see a separation between the orange, the yellow, and the blue. But then when you go to duration, it's pretty much a different story. I would guess maybe that V has a less duration than the other two, maybe, but they seem to overlap a lot on the y-axis, which indicates that duration might not be such a great feature to use. All right, so we're going to test our machine learning model now. And this is our build model section, and I want to actually move back to our slides because we just did feature extraction example, and I want to zoom out and go to building a model and talk a little bit more about what is a classification model before we get into this whole MATLAB and trying things out in code thing. So what a classification model is something that takes data, which we call features, and uses that data to infer a category. All right, so you will take a feature vector, which will have several dimensions. So in this example, we have some data on the color, size, and weight of fruits. And then pass that information into the classification algorithm. And when we do so, the output is one of 3 classes. It could be pear, apple, or blueberry class. And you can think about it this way. Imagine that the color is green, all right? So the color is green. That means that it either has to be a pear or an apple. It could not be a blueberry because blueberries are not green. And then I tell you that the size is, let's say, maybe could fit in the palm of your hand, and it's kind of light, right? So maybe apples are a little bit heavier than pears. I actually don't know, but let's just say for sake of argument. In that case, we would choose pear in this algorithm because pear would be lighter. So that's how the classification could go. Just one example, and that would be more along the lines of a decision tree classification model, but there are many ways that you can build a classification model. And in this case, we're actually going to use a model called k-nearest neighbors. All right, so this is a diagram explaining k-nearest neighbors. And basically, if you have a set of data which is labeled, and in this case, those labeled data would be the blue squares and the red triangles. If you have a set of data that is labeled like that, and you have a new point, which is this green point in the middle, how would you go about choosing the class of that green point? And in this case, you could imagine two variables, an x-axis variable like duration, a y-axis or an x-axis variable like aspect ratio, a y-axis variable like duration for our letter example. And you could say, wow, here's the green thing. It goes in a duration of 2 and an aspect ratio of 2. And here it is in the middle. And what is it? Is it a V? Is it a U? What is it? Well, the way the k-nearest neighbors model works is it looks within a certain radius. So in this black circle, we've set the radius at, let's say we've set the radius at a distance of 5 or 2, let's say 2. Well, it looks in that 2 radius circle and it counts the number of items that are red and the number of items that are blue. And then it makes a determination based on which category has more presence in that circle. It will make a determination that this green dot belongs to the red triangle class because there are more red triangles in the circle than blue squares. All right. And we could adjust this radius. So we could adjust it to be larger. Let's say we adjust it to be a radius of 4 instead of 2. In that case, maybe our model counts now 3 blue squares and 2 red triangles. So it would come up with the opposite conclusion that this green square is or green circle is a blue square. Right? That's a lot of squares and circles and triangles and colors. A little bit confusing, but I hope this diagram kind of helps you understand what is the k-nearest neighbors algorithm. It's essentially taking the nearby neighbors, hence nearest neighbors, and it's taking k of them, right? So let's say in the first case 3, in the second case 5, and it's making a decision based on that. And actually, this is the radius version of the problem, but there's also another version where you just take 3 nearest neighbors, 2 nearest neighbors, 5 nearest neighbors. And Elena says, it's like ANOVA, analysis of variance. In a way, yes, because it is allowing you to tell, an inference about what this is. But it's actually not really a linear model in that sense. It's a little bit different because it's relying on this distance concept, and that's actually the key part of the prediction. But I see what you're saying, because analysis of variance involves minimizing the distance, the errors, and this does too. But in analysis of variance, you're interested in fitting some linear function. So that's the only difference. This is a little bit more of a geometrical concept, but yes, I see the similarity. That's a very good point. All right, so let's implement this in MATLAB now, and I'll share the link so that all of you can see it and access it in your chat. So there it is, the link to our new lesson. And this is going to go on for a little while because we're actually going to dive deep into this model and fitting it to our data. So let me share my screen and show you how we'll start off here. So I've navigated here, and we're going to fit a simple classification model called KNN. And MATLAB has a built-in function for this purpose. It uses the term fitCKNN, and then the arguments passed inside are data and response variable. So data would be essentially the feature list, and then response variable is the target. All right, so this is the class that you want the model to predict. And in this case, we're going to be interested in having our model predict the character based on the features. So let's just load in this features variable here. And you can see it's a 470 by 3 table. So it has 470 characters, each one with an aspect ratio and a duration assigned to it. And our goal is going to be to classify these appropriately. So let's fit a model to the stored data and feature. We'll call the model KNN model. We'll name it KNN model. And we'll use the fitCKNN function. And remember the format of our function. The first argument has to be the data. So we're going to type features. And the second argument has to be the response variable. And if you go back to our table, that category is labeled character. So I'll just type character in here. Okay. And let's hit submit to see what happens. Okay, we got that. So, having built this model, we can now classify our observations. So you can just close out of this. And the way that we do that in MATLAB is to use this predict function. So we can type as our first argument the model that we want to use for prediction, and in the second case, the feature. Helena says, can I ask from where do I get the feature data.mat? If you go to this link, the one I put in the chat, the feature data will already be loaded up. So all you need to do is start typing in task 1 and then click submit, or you can click the run button at the top. So either one would work, but the data is already loaded, so you don't need to upload it to this portal. And the reason I'm using this portal is because it's free to use and really easy to get set up on. If we went with our own MATLAB downloaded version and did sort of a custom workflow there, it would be difficult to get everybody set up with MATLAB. So I think this is the best approach for now. All right, so let's go ahead and move on to task 2, which is prediction. So we're asked to make a prediction variable named predicted. So these are the predicted quantities. And we use the predict function. Our model's name is KNN model. And then we have this new data, which is an aspect ratio of 4 and a duration of 12. So we can now put that in to our model. Oh, I'm sorry, the duration is 1.2. I think that's correct. We might need to do something to the, oh, yes, we need to put it in a list. So just put this data into a list or an array in MATLAB, so-called. And when we submit that, it tells us the predicted category is V, okay? So it's saying, all right, you told me that the aspect ratio was 4 and the duration was 1.2. And I'm going to tell you that based on that information and that information alone, we should have a V here. Okay. Oh, great. I'm glad that worked, Elena. Glad you were able to get that working. And so, yes, that is sort of the idea behind predictions. And there could be some outliers. Check this out. We have a few outliers. In this case, this red dot was a J, and these two blue dots were V's, but they're kind of clustered in the wrong area on the plot. So that can misclassify some of these, because let's say you look at this, there you have something over here. It should clearly be a J based on just visually looking at it. But because there's these outliers here, the model might think that it's a V, right? So we need to think about that too. And we could expand the number of neighbors in order to reduce this error. So what we do is we'll build a new model called MDL. And, well, actually, let's just build, sorry, weird. I got a little disconnected there. Oh, there it is. It comes back. Excellent. So we'll just build KNN model again. And we'll copy all the code from task 1 and all the code from task 2. And now we're going to type num neighbors and 10. Oh, sorry, and 5, I suppose. I don't know what's going on with my resource here right now. This is a little strange. Is anybody else having any connection issue here with this? I hope not. I hope you're not having any issue. But let's quickly go so that we don't lose it again. I'll go kind of quickly. Click submit. Hopefully that loads in time. Maybe, no, that's correct. I think it might be breaking down a little bit, my environment. I'm not sure why. Because I did pass in the correct number of arguments. Oh, sorry, I forgot to put num neighbors again. That's what happens when you get closed out of your work and you lose track of what you're doing. All right, so that worked. And so if we now look at our category predicted, we predicted J. All right, so let's look at this actually on the data itself. We can go back to this outliers thing. Try reloading. I think it should give us this little picture again. Let's see. Hopefully it does. All right, I guess it didn't. But we're getting a different answer depending on what number of neighbors we use. And what did I write in task 1? So in task 1, I'll copy the code into the chat. It was just KNN model equals fit CKNN, which is the function we use to define a KNN model in MATLAB. Yep. And then in this function, we have 2 arguments, which are the features. So those would be the duration and the aspect ratio. And then the response variable is the character. So basically, we're asking the KNN model to predict which character based on only 2 things, the aspect ratio and the time it took for the letter to be written. Okay. And then we reduced the number of neighbors from 10 to 5 in task 3, and that sort of has caused a different prediction, probably more sensitive to outliers in that case. In fact, we can test that right now. So we know that we can get the predictions and the features. Oh, I don't need a comma here. Sorry about that. Oh, I think I need a comma here. All right, maybe I'll just delete this for now, and we'll just look at the predictions for this. Oh, I understand why. So we need to make a new variable, predictions. And let's actually build a 2 model system. So we'll have another model. So this will just very clearly write num neighbors 5 or 10. And we'll call this KNN model 10. And then here we'll do KNN model 5. So the only thing we're changing here is that we're going to change from 10 to 5. We'll call this predictions 10 and predictions 5. And then we're going to type predictions 10, predictions 5, and features.characters. So we can see that they basically agree on most things. Let's see if we can spot one that they don't agree on. In theory, there should be. Oh, here's one. So line 29. Predictions 10 thinks it's a M. Predictions 5 thinks it's an M, but actually it's a V. That's interesting. But is there, oh, and here's one. Predictions 10 thinks that there's an M. Predictions 5 correctly gets that there's a V. Oh, thank you, Helena. Now you can see this example. This is line 41, you can see. Where predictions 10, where we have 10 nearest neighbors, that one says it's an M, but predictions 5 says it's a V. So in this case, the 5 nearest neighbors is better than the 10. Okay. Let's see if we can find another one. Here's another case, 44, exact same case. But most of the time they do agree. It's just those couple situations where they don't agree. Let's see if we can find any case. Yeah, here's another case, BJJ. So it looks like predictions 5 is generally faring better than predictions 10, because sometimes predictions 10 get something wrong. And I think it's because it's considering too much data. So it's considering points that are really quite far away from our predicted, our target. And those points could be outliers. Here's another case, VJJ. So you can just play around with this sort of thing. I'm not going to go through the rest. We went through about half of them, but you get the idea here. So let's go ahead and go to the next section. Oh, before we go to the next section, I think I'll send this to Helena. So this is the data. And to get to class 3, all you do is just click on class 3. So make sure that you are in this exact link, the one I just sent in the chat. and click on task 3 on the left-hand panel, and that should get you to task 3. But if you can't, for whatever reason, you can just type it in further practice. It's the same thing as task 1, but we're adding a new parameter. We call these hyperparameters because they are values that change the behavior of the model itself. And we're changing that hyperparameter to, say, 5. All right, instead of 10, which is the default hyperparameter. And we're actually now at this time going to go back to our slides because I want to talk to you all about another concept. And this is what we call the confusion matrix. Okay, so a confusion matrix is a way of describing how well a model agrees with data. And it's particularly useful for classification algorithms like the one we have here. And on the x-axis, or on the columns, we have our predicted conditions. So our model might predict several things. For example, it might predict a positive outcome or a negative outcome. In this case, our model would predict J, M, or V. And then in the rows, we are showing the actual conditions. So in those rows, we have the real value. So if it's a J, M, or V in the data. So when those two things line up, and let's say the model predicts a J and it really is a J, that's what we call a true positive. Because it means that the result truly was the predicted value. And then we also have a concept where they don't match up. And those are called false values. So for example, if we say that it's a J, but it's not a J, that's a false positive. And if we say that it is a J, if we say that it's not a J, but it really is a J, that is a false negative. Okay, so confusion matrix can be really helpful for seeing the strengths and weaknesses of your model. And I'm going to demonstrate that now in this next workshop section. So you're going to go to the next section of the workshop, which is lesson 6. And I'll paste that in the chat. So this is lesson 6. Yeah, exactly, Elena. So you said it like a hypothesis test. This is super simple, similar to a hypothesis test. And I can tell, Elena, that you have studied statistics because you have a lot of good knowledge about statistics. And in fact, that's very helpful for machine learning because a lot of these things are very similar. But yes, so you might have seen this in your statistics class. And in fact, we're going to use it to help understand our machine learning model. Okay, so let's go ahead and talk now about machine learning, and we'll talk about the confusion matrix in the context of machine learning. So I hope you can see my screen now. We're building our little environment. And remember, folks, the link is in the chat for this, and also was up on the screen just a minute ago if you want to rewind and grab it. But for task 1, we're going to actually look at these and see how well they have compared. That's what we were getting at a little bit in the previous workspace, but now we're going to make it a little bit more concrete with this confusion matrix. So we classify the letters in the table test data by using the predict function with the trained model, KNN model, and we're going to store those variables, those predictions, in a variable named predictions. So we type predictions equals, all right. Then we type predict function, and the first argument will be the test data, right? Because that is the features that we're interested in analyzing. And then the second variable here is going to be our model. So we're going to use the KNN model. All right. And so if we submit this, it should work okay. Oh, had a little bit of a mishap here. Oh, I think I have to reverse the order of these. Sorry, everybody. It should go model first and then test data. I forgot about that. We just did that too. Sorry, everybody. But there we go. So we get some 10 different predictions from our model. And now we can compare the predictions to the known classes by using the double equal sign operator. So this is what we call a comparator. So comparator is what this is. And in this case, the comparator is equivalency. So we're looking for whether the values are equivalent. And so we can write this new variable is correct. And we have predictions and our double equals. And what do we want to compare this to? Well, we want to compare it to our test data because those are the true values. Those are the rows in the confusion matrix, and predictions are the columns. So we're right now looking for what we would call true results, true positives or true negatives. In this case, we have multiple categories, so they're kind of the same thing. It's just true values. All right. I guess we've made a mistake here too somehow. Oh, right. It's only the character. Sorry about that, everybody. This is what you get with live coding. All right, so the reason that didn't work is just because we don't want to compare to the whole table. We just want to compare to this last value, which is not the whole test data. All right, now we will calculate the proportion of correct predictions by dividing the number of correct predictions by the total. So we can just say accuracy and the sum of is correct will tell us the number of entries where the prediction matched the character in the test data, so the category, the response variable. So we do sum is correct divided by num_L, which is, we're told that is the function to determine the total number of predictions. And so we can just write prediction. All right, so we can see that our model has an 80% accuracy when estimated over this test data. Oh, sorry about that. I'll remove the hover. Thank you again. All right, so hopefully you can now see. I'll just leave this up for an extra minute so that everybody can see what's been written so far. So we wrote accuracy equals sum is correct, which tells us the total number of true or correct results. And then we divided by the total number of predictions to get 0.8. And by the way, this would be that value which would lie on the diagonal of the confusion matrix. It's all of those values where the prediction matched up with what we actually have in our data. And an 80% accuracy is, I would say that's good, but not great, really. Maybe you could even get an 80% accuracy with a simple linear regression. I don't know, but I wouldn't say that 80% accuracy is anything to write home about for, at least for this task. Maybe if you're trying to do something very complicated that has never been done before, then 80% would be great, because that's higher than 50. But a 50-50 shot, or in this case, a 33% shot. But for most applications, like for this letter detection algorithm, I would say 80% is not a great result for our letter detection algorithm. But it's good to help us learn how to do this. And we can build this simple model to help us learn. So now we're going to look at the misclassification rate. Okay, And so the misclassification rate can be calculated with a different comparator. This comparator is the non-equals sign. Yeah, so Ellen asks, what do we actually predict? Of course, you can ask a silly question. That's no problem. It's not even a silly question. It's a good question. What do we actually predict? I had been out of my head with setting MATLAB, and I did not understand for what we make predictions. Good question. So we are currently making predictions of the letter. So we have three letters, J, M, V, and we're predicting which letter it is based on the aspect ratio and the duration. So aspect ratio refers to the relative size of the X and Y axis for the purposes of the character. Duration is how long it took to write the character. So we're asking the model, hey, if we only give you these two pieces of information, right? If we only give you aspect ratio and duration, then is it possible for you to predict what character it is? And the model said, well, I'll try. So it said for the first one, J, I think that's a J. The second character, that's an M. Third, that's a V. So it actually is doing pretty well until it gets to the fifth row. And look, it says, instead of saying that that's an M on the fifth row, it says that's a V. So it didn't classify the letter correctly in that case. All right. And so that's why we have an 80% accuracy rate, because in some cases, the model was unable to predict the correct character given the data that we have in our feature list. All right. So hopefully that helps you understand a little bit better. And now we're going to move on to our misclass rate, which is quantifying exactly this. When do we get these things wrong, right, in our model? So let's type misclass rate equals, I guess we're going to type the rate. So we could use predictions not equal to test data.character divide by predictions. Do you want to guess what the misclassification rate will be here? Keep it in your head of what you think it might be, and or chat it out. But the misclass rate is 0.2. All right. All right. And so Elena says we basically did not train it, and we can say it is a supervised model. It is. That's exactly right. This is a supervised model. So excellent job recognizing that. The reason it's supervised is because we are giving it the response variable. So we're giving it the categories, and we're saying, this is the category. Can you figure it out on your own if we tell you, right? And training it towards a very specific goal. So for that reason, this is a supervised model. We did train it, though. That's the only thing there that is not quite right. We did actually train this variable. We trained it using the KNN model, and we did that in the last module. So now we're testing it. We're testing its accuracy. All right. And can we increase these accuracy rates in MATLAB? Absolutely. We did that actually with the number of neighbors. So if you go back to our previous module, what we did was we looked at two different KNN algorithms, one which had number of predictions at 5 and one at number of predictions 10. In this case, we're using the 5. So we actually already did improve it. Let's go back to 10 and see what we get. Oh, actually 10 is even better. Look at that. 90% accuracy. So you could say that by adjusting these hyperparameters, you can get an even better result. All right. So let's go on to the next task. And here is our confusion matrix again. So remember, we have two axes to the matrix, true class and predicted class. When these things match up, we have a correct or true prediction. When they don't match up, we have a false prediction. Okay, so let me get rid of that. Oh, so we will be doing task 4 shortly. Oh, actually, we did task 4 already. It was misclass rate equals the sum of predictions divided by number of length of predictions. Yeah, here it is. I'll paste it in the chat as well if you need it there too. All right, so yeah, thank you for keeping track of that. So we will now do the confusion chart. So to do the confusion chart in MATLAB, it's really easy. You just type the words confusion chart. And so we're going to compare the predictions to the test data characters. So we just type predictions and then test data characters. That should give us our confusion matrix. Oh, maybe we need to reverse these. Let me check. Ah, yes, they need to be reversed. Sorry, everybody. I keep flipping them in my in my explanation here. But when we type these out, maybe it's character, not characters. Oh, that was actually the real issue. It wasn't that they were flipped. It was actually that it was the wrong variable. So it's test data.character. So I'll paste it in for task 5, the correct code. And you can see our confusion chart now on the right-hand side. So if you see here, if our true class was J, and our predicted class was also always J. So 4 times we had a true J and we got it right. So that's great. And that was our best letter, actually, J. Getting J right. Then there was a problem if we had our M's. So our M's, in one case, the prediction actually said that it was a V, not an M. So that's pretty bad. And then in the last case of our V's, this was probably the worst one because the true class was V and only 50%. I mean, there were only 2, but only one of them they actually got it right. The other one said it was a J. So you can really deeply dive into what are the misclassification rates for different letters and different scenarios by using these confusion charts. Okay, so the last thing here says investigating the features of commonly confused classes can be useful. So we can do a logical array of the incorrect classifications to index into test data and predict to obtain the data from those classified observations. And we could do this, but I think we've already kind of looked at it through a confusion chart, so I won't get into that more. All right, so that's good. Actually, I don't want to go on to the next lesson. I want to go back to our slides, and we're going to do a quiz together. So I want you to take this quiz. I'm going to paste it in the chat as well. This is to test your knowledge. So I'll give you a couple minutes to do this quiz. All right, everybody. So we don't have any responses for the quiz yet. So I'm going to go through and cover the answers. So let's go through. So the first question is, why is it important for your data to have large coverage over the feature space? And the answer here is because you need to avoid overfitting and avoid issues with extrapolation. So extrapolation is what happens when you don't have really a lot of data to go off of, or any even data to go off of. And so you kind of have to use points that are not really the same, but just use your best guess to get that. For example, let's look at the stock market. If you have data about the stock market from the past year, and you want to predict the next upcoming year, that's pretty hard because it's an extrapolation problem. But if I know the beginning of the year and the end of the year, and I want to predict the middle of the year, that's interpolation. So we have some coverage over the future and the past, so we can avoid those issues. And as far as overfitting goes, overfitting is what happens when your model is way too specific to a small subset of data. So if we get a large coverage over the feature space, we get many different examples with different variety of features, we will avoid that problem. Okay, and then I asked, what is feature extraction? Well, feature extraction is distilling a data set with a potentially large amount of features into its essential information needed for prediction or classification. So think about the letters that we had. So each of those letters had so much data at the beginning, X, Y, P, time, and each of them had many rows, maybe even like 50 rows each. Now, each letter only has two numbers, aspect ratio and duration, and we were still able to build a reasonably good model out of that with a good decent accuracy rating. All right, and now we said name one argument, at least one argument, accepted by the k-nearest neighbors algorithm. And one argument was the category, so we need some sort of response variable or category to predict for. It is a supervised learning algorithm, as Elena pointed out in the comments. And then also we need to give it a search radius or a number of nearest neighbors. So in this case, we're giving it a number of neighbors, and we're saying 5 or 10. Okay. And this question was, what is a confusion matrix? So a confusion matrix is actually all of the above here. It's a way to represent the accuracy of the classification algorithm as applied to a particular data set, typically your test data set. It's also a matrix designed to show where your model is potentially getting confused. So remember from last time, our model did great on J's, but it didn't do as good on M's or B's, and we figured that out through the confusion chart. And finally, it is a way of categorizing false and true and positive negative results. So we can calculate the true positive rate, the true negative rate, and all of those things. So that's how we use the confusion matrix. And so imagine that we want to use our model in the real world to classify the drawings of any letter. What are some important next steps to improve our machine learning approach? So one really important thing would be for us to increase our coverage of the feature space. I think that will be the best way to do it. And actually, we will get into that in the next section. So just stay tuned for that. Let's go back to our slides here. So we're actually going to have a 5-minute break since we've been going for a little while now. And then we will return and we will do some data pre-processing. So this is how we're going to get multiple files from our letters into the data set and help us build out our machine learning skills in MATLAB. So after about 5 minutes, we'll come back here and take a look at that. But until then, see you in a bit. All right, everybody. So I hope you enjoyed that break. Sorry, it took me a little bit longer. I wanted to go make some coffee. But yeah, it's great to be back. And we're going to be going on now into sharing our data store. So data store is a repository for collections of data that are too large to fit in the memory. So in machine learning, this is a really common problem, actually, where your data is super large relative to memory. I think the largest memory, like RAM systems that you could use as just a normal user, they're usually going to be only maybe at most 50 gigabytes or 100 gigabytes at the absolute most. But there are data sets which are significantly larger than that. By the way, when you build a model, the model itself can often be a large memory use too. So if you think about a random forest model, and let's say that there are 1,000 features, well, if there's 1,000 features, then those models will have to create thousands and thousands of trees. So you can see how things end up getting really big really fast. And to help to limit that memory overuse, data stores were invented to sort of read in your data bit by bit. And actually, it's not a new concept to machine learning. Buffers have always existed because there's always been this tension between storage and memory. Elena says, how do we allocate a data store? So actually, we'll go over that right now. We're gonna spend some time looking into data stores, but I just want to talk a little bit more about this issue because the concept of a data buffer. Let me actually use this on Wikipedia. The concept of a data buffer is really about storing data temporarily while it is being moved from one place to another. So in this case, we are storing the data on a physical storage medium. So usually the data would be in the cloud, or it could be on your personal hard drive. And then we want to implement them because RAM, which is our fast memory, that can temporarily store data. And this is really useful for machine learning because you need to have that data readily accessible. And RAM, though, is much more expensive and also more difficult to maintain. So that's why there's always this tension. Otherwise, we would just put everything in RAM and make the RAM huge. But unfortunately, we don't have that option. So do we use heap? I guess I'm not sure what you mean by that. I think I know what you mean by that. I don't actually know. I think it is a heap mechanism, but I actually don't know. So sorry, I don't know the answer to that. Yes, I believe we do allocate using heap, like a heap-like method, but I'm honestly not sure what MATLAB will do. That would be a good question, though, for MATLAB. Maybe I'll look into that a little bit after this workshop. But yeah, so we'll test the data store in MATLAB. We're actually going to implement this. Maybe this will help give a little bit of light, shed a little bit of light onto some of those questions about how it actually works. So let's go ahead and paste this in. It's going to be it's not going to be a static allocation of data in one sense. It's not going to be like we just put in a fixed amount of data. It's going to sort of dynamically go through the data set and put an amount of data in the RAM that is not going to overload the memory. And we call it batches. So we'll allocate in batches. But that's a good question. All right, so let me go ahead and now share my screen so we can all look together at this data store code. Paste that through. And I'm going to remove the link from the display so that you all can see. But yeah, you can use wildcards to create a data store to any files or folders that match a particular pattern. So we have some handwriting data, and each handwriting data is stored in a TXT file. If you remember, these files can be quite large. They have X, Y, pressure, and time, and that's for just one letter. So we're going to build a data store to store this, to read in this data as a buffer. And we use the asterisk. The asterisk means that it will be a wildcard. So wildcard tells us any values can come after this data and before this period. So you could have this sort of file, right? And so actually, I think we want to use user here, not data, because if you remember, the form of this file is user003b2. Oh, they all have M in their name, sorry. So we will write a wildcard at the beginning and then M. So this is just saying anywhere in the file, as long as it says M, we'll go there, and we'll call this letter DS. So let me save this and paste it in the chat for you who are following along. And we'll submit this task. Oh, I guess that's not quite right. I wonder, oh, it's because it's ds.xlsx. I meant to say this, sorry. I'll repaste that in. Shouldn't have pasted it so soon before we got through. Cleared our category a little bit too confident in the live coding. But yeah, now we can use the read function to import the data from a file in the data store. So we'll say read ds. Remember, this semicolon just prevents the cell from returning that data right away. It'll just store that in our workspace, but it won't just return it right off the bat. So we'll replace ds with letter ds in this case. It should work. And now we can visualize the data by plotting the x variable of data on the horizontal axis and the y variable on the vertical axis. So we'll just type scatter data x, data y. Let's see how that works. All right, it looks like it worked. So we can see that we have our x variables, our aspect ratio, or duration and aspect ratios here. All right. We're going to call the read function again, and that will import the data from the next file in the data store. Oh, sorry, this is our drawing. I'm sorry about that. So let's import and plot the data from the second file. So we're just going to call the read function again. And we're going to plot it just like we did last time. And we'll hit submit. And now we get another piece of data here, right? So it's just another user's writing. And now we can use the read all. So if we write data equals read all, we could read every single letter with an M. So these are all M's, or supposed to be M's at least. Let's see what happens if we read in all of these files and plot them. Okay, we get some kind of crazy mesh of all this data. And the further practice is try importing everything for file V. So let's try this. We just replace the M with a V, click run, and indeed we get the same sort of thing. And so yeah, it's kind of interesting that all the V's sort of get a little offset from each other, get a little distorted from each other. Kind of interesting. But okay, so let's go ahead and now move to the second part of our data store lesson. We'll just skip this part. Part 2. And then, oh, I'm sorry, not part 2. We already did that. We'll do the pre-processing function. So I'll paste that in the chat for you all to check out. Let me share my screen so I can show you all. We can all look on together. And we're going to build a function called scale at the bottom of our data. Okay, so we'll build a function called scale. Just put it in this bottom cell, tasks 1, 4, and 5. And the way we define a function in MATLAB is we type the word function. It's pretty simple. And then we type the output. So the output, we will output data. And we say equals scale. That's the name of the function. And it will also take a data input. And then what we'll do is perform these operations. Let's just copy and paste those in here. So the first operation is that we're going to make the times into seconds. We did that already in part 1, but we're just making it into a function now. And then we scaled by 1.5 the x-axis. And we also did that in part 1, but now we're just doing it more in a function in a little bit, make it a little bit easier. Sorry, I just put that in the wrong way. And then we return our data. So we just end this function. All right. So now we'll type the next task. And you still need to call your function manually, but we can actually automate this by using a transformed data store. So let's try that now. This way, everything we read in will look the same. All right, so this is task 2. And we'll write preproc ds. So this is going to be our preprocessed data store. And we call the transform function for this. And so our data store's name is letter ds. And the function is at scale. So we use at scale for that. All right, so now all of our data will be transformed when we read it in. And we can do our same read all for this that we did last time, where we import everything by the read all function. And we should be able to plot time and y. I think that's right. Let me just double check before I run it. Yep. It actually says we should do plot, but scatter would work just fine too. But we'll just do plot to keep it consistent with what they have. And you can see all of our data is now looking very similar. Okay. You did see, though, that the location of a letter was a little bit different. And so, again, we want to normalize our data to correct for that. We shifted the mean and scaled to a fixed range. So let's do that. We already talked a little bit about normalizing data. But in this task 4, we will do that. So I'm just going to put it in this bottom piece here. Oh, Maybe I won't. Maybe I'll just put it in further practice. No, I will keep it here. So we will modify and we will add to this scale. We will shift the X and Y data. Right? It does make a blank plot though, and the reason is because some of our data is now NaN. So you notice in our data set we have some NaN values when there's no when it's not on the screen. So we can use omit NaN in our means to fix that. This is similar to like a NaN mean in Python. Yes, the function in the last test. Yeah, thank you. Exactly right. So we just modify that last bit. So now if we visualize these last ones, you can see them on the right, bottom right corner. They're all around 0. Okay, so this is just giving you a little practice with data store if you want to amplify your stuff. All right, and now I have one last quiz for all of you. Oh, great, another quiz. Sorry, everybody. But we're just going to have another quiz, and I'll give you 2 minutes to look at that. All right, everybody. So we had a couple responses. So thank you to everybody who filled out the quiz. And we're going to go over the answers now. So first question was, what is a data store? And the answer was that a data store is a buffer object that allows you to read in data incrementally, which avoids memory constraints. And that's so, yeah, great job answering that. A couple of you said a central location to view and shop for data sets. That would be great. Actually, there is a website like that. There are multiple websites like that, but I'll just paste one that's kind of popular, which is kaggle.com. This is a great place where you can view and download data. I don't know if any of them are for sale. I don't think so, but it is a centralized location for machine learning oriented data. But yeah, thank you for getting that one right. And then we had one question here. Why could it be necessary to transform values in your data set? And the first response option was to ensure that they are all of the same order of magnitude. The second was to allow machine learning algorithms to efficiently learn weights and optimize towards a solution. And the final one was to find more meaningful features that could improve the ML algorithm. And the answer is actually all of the above. So you all got this right in a sense. Nobody chose a wrong answer. But yeah, you could say that for any of these cases. So that's why learning to transform variables, and honestly, this is a really difficult aspect of machine learning, supervised machine learning. So it's something that still requires a lot of skill and a lot of tinkering. But yeah, thank you everybody for doing that. So we have one last workspace that we're going to go into. We'll dive into this last workspace. It's more machine learning practice, and we're gonna do a little more machine learning practice and actually get going on this. Oh, this doesn't actually bring us anywhere. Sorry. I'm not sure. Let's see. I'll get the right link in a second. Just give me 1 second to get the right link. Okay, now I have the right link, so I'll paste the right link in here. And I'll edit my files too. Actually, I don't think I can. Unfortunately, I don't think I can edit my slideshow to show this, but hopefully you can see that link. And if you go to that link, you should be able to get to there. Yeah, this is really more of an activity I want you all to encourage you all to just look at this on your own after our workshop is over, since our time is coming to a close. But this is a way you can integrate all of the different things we've learned about today. We learned about transforming variables, using our data store. We learned about the KNN model. And this last module is just showing you how to sort of think about all of these things together. You all can see I'm dealing with a little bit of an issue setting up the course. Let me try refreshing the browser. Maybe that will work. Sometimes that works. You never know. If you just refresh. Well, maybe we won't get to do this task, unfortunately, because the connection's not cooperating with me, but I highly recommend you to take a look at that. And we will do one last quiz, which is a wrap-up quiz. And this one is just designed to get a sense of what you took away from the workshop. So the question is, name one thing that you learned about MATLAB and or machine learning during this workshop. All right, folks, so we have a couple of answers here. KNN model, KNN algorithms, finding the accuracy score, and classification. So excellent. I'm glad that you all were able to take something away from this workshop. And I encourage you to look at that last module. I hope it's working for you. It's kind of strange that it wasn't working for me. I tried for quite a long time, but just wouldn't load. But anyway, thank you so much for joining and for participating. I really appreciate the participation in the workshop. It makes me feel a little bit less lonely coming up here and talking. So thank you all for that. And I hope you have a great rest of Global Hack Week. I'll see you tomorrow. I'm going to be doing the daily digest. So I'll see you all next time. All right. Bye now. Bye.